Okay, so Jared started the recording. Perfect. All right. Thanks, Jared. Appreciate it. All right. Okay, so let's get going. So today's section, things get a little bit confusing today. Certain sections we will reach today it's a bit like brain teaser stuff, which really I don't like so much, but that's okay. We'll work through it together. And I've got the module manual open just in case we get stuck. We can go back and look at stuff. Okay, so the last thing we did, we started truth tables and we just did a few examples, reaching one slightly, which is nice. We've covered the important stuff. Now we look at deductions, okay, which is basically another way to introduce truth table in different context. So a deduction, we'll just go straight into an example here. A deduction involves an argument, right? We made a little list here somewhere. Let me just go back to it. Somewhere here about these things, and we said we'd use it at some point. This thing here, right? Argument. And so we're going to use this today, where we say an argument is made up of two different things or two different subgroups of things. One of them is called the premises. The premise or premises, depending on how many we have in the argument. That's this part. And the other part is called the conclusion. Oh, admit, okay. Yeah, premises and conclusion. So if we get a situation where the premise or the premises are all true and at the same time the conclusion is true, then we say the argument is valid. All right, that's the point of this little thing that I've drawn here, this little diagram. It gives us all the information we need for the section we're about to use. So just take a mental note of this little diagram here, or maybe take a picture, write it down. It's a little thing we need to remember as we go along. It's written in this paragraph to the left under the heading arguments, but this is just a summarized version of that. I'll say that again, an argument is made up of premises and a conclusion. If the premises and the conclusion are true at the same time, then the argument is valid. So that's what we're going to test now with specific examples. All right, and let's go straight into this example that we saw at the bottom. Where were we? We did this deductions, okay. So they give us this series of sentences here, and apparently this is we need to check if it's a valid argument, basically. All right, so it says, if Edith eats her vegetables, then she can have a cookie. Edith ate her vegetables, therefore Edith gets a cookie. All right, so this is the thing that we have to construct into some kind of combination of statements, like how we did before, make a statement and then we can make a truth table out of it. So they've given us labels to use for each thing, which is helpful. Usually we have to do this by ourselves. So we're letting the label P denote Edith eats her vegetables. And Q says Edith can have a cookie. Right? So I'm not sure why they wrote it like this. I'm just going to rewrite this at the bottom. So the statement above first says, if Edith eats her vegetables, then she can have a cookie. So that's if P, then Q, right? According to the labels at the bottom. Let's just check. If P, then Q. Yep, that's fine. So to write a deduction rule, I'm going to write this at the bottom like this. If Edith eats vegetables, then she can have a cookie. That's the first part. Then the second part, the next sentence basically says Edith ate her vegetables. Right, so that's saying, which one is that? That's P. So that's saying, no, sorry, that Edith ate vegetables. Yeah, that is P. So P is here. I'm not sure why they have Q there first, but it doesn't matter. Therefore, Edith gets a cookie. Oh, no, no, sorry. They just wrote it in a weird way. So just make sure you can see that this, I'm not sure why it's in this format, but yeah. So it's fine. It's fine as we're doing it. So as I was saying, after the full stop, let me just take that from the top, right? If Edith eats her vegetables, then she can have a cookie. That's this part that I've written. And after that sentence, it says Edith ate her vegetables. That's just P. That's why I wrote P at the bottom. Then the bottom part, we just put a line here and we say, therefore, Edith gets a cookie. So that's Q. So this is just a way of writing what's in the sentence above in a sort of mathematical format. Yeah, so the therefore is very important. That's like the, not like, that is the conclusion. Right? Whatever's on top are the premises. What's at the bottom is the conclusion. Okay, so formulating this is the first part. Then from there, it's quite straightforward. We just need to make a truth table for this, which I think is done at the bottom. Let's just take a peek. Yeah, it is, but we're not going to look there yet. We're going to do this by ourselves, right? We'll check our answer once we're done. And then I'll tell you why we're doing this, right? I mean, of course, we're checking if this is a valid deduction. Remember, deduction rule is valid if the premises are true at the same time the conclusion is true. Right? So in other words, we need to find a place where this is true and this is true at the same time. To the truth table to check that. So let's see what we can do. This is going to be a straightforward one as well. We got a P, we got a Q, we got a if P then Q. Those are all the things we have in our rule, so we can fill that in without any trouble. This is a bit of a recap as well, I guess. Okay, so you guys remember the usual story. The P and Q, just give them all possible values here of true and false. So I'll do it in this way: true, true, false, false, true, false, true, false. Change color for this. Okay. Now, an implication is true if P is false or Q is true. So again, we just go through each row and check where we meet one of these conditions. Maybe I should write it above the actual P and Q here, right? To make it look more easy to match. So as I said, we need P to be false or Q to be true. So let's see where we match something here. Well, if we match any of these conditions, it means the implication is true, right? That's just a recap of last week. So the first row here, do we match anything? Yes, we match the Q. So it's good enough to say true. Second row, do we match anything? We match nothing. So we'll say false for that one. Third row, do we match something? Yes, we got a double match, even better. So we say true. If we get just one match, it's good enough. Okay, last row, do we match something? Yes, we do. We get something here. So that is true. Okay, so this is what we need to use to check whether the deduction rule is valid. And it's valid again if whenever both the premises are true, or however many premises we have, if all the premises are true, when that happens, we want also to see that uh, the conclusion is true, right? Yeah, so we just need to identify which is which here. Maybe we should do that above here. Let's identify them. So premises, let's just make color for that. Let's make that a yellow color. Which are the premises here? This is the first premise, right? The other one is P. So these are the two premises. Q is the conclusion. So let's call that C. Gosh, call it C. So can we identify a place where the premises are true? That's only here, right? This one, there's a premise that's true, another premise that's true. Everywhere else, they're both not true. And in this case, when the premise is true, is the conclusion also true? Yes, it is. So that means the deduction rule is valid. So that's the kind of thing we need to look for. Let's just double check the answer at the bottom here. True, true, true. True, false, false, false. Yeah, okay, looks good. Looks good. So this is the thing that we need to do. Okay, anyone has any questions at this point? Of course, we'll do more examples. We will do a few more, but in the meantime, anything unclear, check the comments. Yes, Creole, that's correct. The truth table is always there. So we can always bank on this thing coming out. Usually, yeah, usually it comes out in a straightforward way, sometimes in the form of a deduction rule as well. So these are probably the two most important things in this entire learning unit. The next section, which we will see the proofs, is usually not that often it comes out, but it does sometimes. So anyway, we won't leave anything out. Right, so here you guys can see a summary of the explanation we've given, and you guys can read this in your own time if you forget what I said. All right, so this is it's a nicer one because they give us the mathematical structure already. We don't have to work it out from some sentences. And they ask us, is this a valid? So of course, the easiest way to do that is to just construct a truth table. So let's do it. Yeah, let's see. We don't need too many things here as well. There's only two variables involved. So as you guys may remember, two variables, 4 rows, which seems to be the most common number of rows we work with. Two variables here, just P and Q. So let's start by writing P, Q, maybe a better Q than that. And we need a not P at some point because that's going to be used. And we need we need two implications now. One for the regular P or the Q and one for the not P and the Q. Okay, so again, remember the top has our premises. So this line on top here, this is a premise, this is a premise, this is a conclusion. All right, so anyway, we'll take note of that later when we finish the table. So let's get the table going. We have 1, 2, 3, and we'll make a fourth one at the bottom. So 4 rows here. Let's quickly fill in the basics. True, true, false, false, true, false, true, false. Not P is just the opposite of P. So when P is true, not P is false. When P is false, not P is true. Okay, I should have done that in a different color, but it's fine. That's a basic one. Implication. If P, then Q. So we need P to be false or Q to be true. We need that to be met in order for the implication to be true. Let's see where we meet that. First row, we meet it here. Second row, we don't meet it anywhere. Third row, we meet it 2 times. Fourth row, we meet it once. Okay, so that means this is true, this is true, this is true. The one we didn't meet is false. Okay. Now again, I'm doing this in a weird way, but you guys can do this however is most comfortable for you. I just find this matching makes it a bit less likely you'd make a mistake. Okay, now we have a not P with a Q for the last implication. So the not P. So the first part needs to be, let me just think for a second. P false or Q true usually. So the not P is the first part. So the not P needs to be false or the Q needs to be true. Again, you guys can double check these rules at some point. It's not always easy to remember them, but doing a few examples, you will eventually remember them. Okay, now let's try and match these. The Q and the not P with what I wrote above. So the Q matches here, first row immediately, and so does the not P. So we match both there. Second row, do we match? We got a single match here. Third row, we have a match for the Q. And fourth row, I don't see a match. So this will be true, true, true for the 3 that matched, and there's no match at the bottom, so false there. Okay, so the truth table is filled in. Let me just take out these rules above because we don't need them. I should take out the circles as well, but that's a dangerous game. I might erase something important, so I'm just going to leave it there. And now let's identify the premises and the conclusion in this slightly ugly green, but that's okay. Okay, so premises, this is one of them, that implication. This other implication is another premise. The conclusion is just Q. So let's first identify a place where both premises are true. And I see that in the first row and in the third row. So we have to check both these places. It can't only happen in one place. It must happen in both places. That where we found the premises true, in both those cases, the conclusion must also be true. and the conclusion is Q here. And I think we can clearly see that in both is true. So in other words, we've got a true for this conclusion as well as a true for these premises. So all three are true. And the same is true at the bottom here. True for that conclusion and true for the premises. I hope you guys are understanding what I'm trying to get through here. I hope I'm explaining it well enough. Okay. All right. So do we do more examples? Yes, we do. PQR. Of course, we have to do one big one with 3 variables. Okay. If you guys don't mind, I just want to quickly check this one as well. Of course, we know it must be right, but we don't have to check. Okay, let's just see very quickly. This example was pulled out from here somewhere. Is this the one? Truth table looks the same. Yes, so I just want to see the word valid. Argument form is valid. Okay, perfect. All right, so that's good. So you guys see what I'm doing? You can also go back and check the module manual if you get confused. All right, let's do this big one now. Okay. That's what I wanted. Let's move a little bit further down. Okay, there should be enough space. Let's see. So we have P, Q, and R. We have 3 premises this time and 1 conclusion. So let's start as we always do by stating first the simplest version of the variables, P, Q, and R. Then we can go straight to the implication. Actually, we can do all of them now. We don't have to do any more sub things. So if P, then R, we can do that. If Q, then R, and P or Q. The downward triangle, was that an or? Yes, it was. Okay. So let's do our 3 variables, so 2 to the power 3 rows, which is 8 rows. So here's the first. It's 1, 2, 3, 6, 7. Do we have space in 2, 3, 4, 5? Okay, yeah, we can fit here. All right. Pull in the P, Q, and R quickly. True, 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 true. False, 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 false. And just alternate the next one. True, true, false, false. True, true, false, false. And then full alternation of every one. Just trues and falses. Okay, that gives us every possible combination. The first implication, let's do this one here quickly. PR, so P needs to be false, or R needs to be true for the implication to be true. Where do we meet that? I'll do this relatively quickly now. We meet here. Okay, second one, we don't meet anywhere. Third one, we meet here. Fourth one, we don't meet anywhere. I'm just trying to be careful as well. It's easy to mess up. Next one, we meet here. Both actually, doesn't matter. We meet here. Next one. Okay, all these we will meet because these are all falses. On this side, it doesn't matter, but let's just pull it in. Okay, so we got a true for every place where we met something. Here as well, here as well. And everything else will be false. Okay, I always hesitate to go fast because it's easy to make mistakes, but we have stuff to do today. Okay, let's do the Q and R. So Q has to be false, R has to be true. So where do we meet these? We have one here already. Second one, no meet. Third one, we meet them here and here. Next one, we meet by the false. Next one, we meet by the true. Then we have no meet for the next one. Yeah, okay, and then we get the two falses, of course. Okay, so everywhere we have a circle, I'll say true, 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 true. Okay, everything else, just making sure. Yep, everything else is false. Okay, one more to do, and this one's not so bad. It's just and or between P and Q, so that we don't have to do any circles or anything like that. What color can I use here now? I don't know. So weird purple here. Let's go with that. P or Q. So as long as something is true between those two, is true. So we just need one true between P and Q. First row, we definitely have that. Second row, we definitely do. Third row, P is true, so that's good enough. Fourth row, we have one. Yes, yes. And the last one is all falses, so no, we don't have it. Okay, so where are the premises here? Let's just identify them. We have one up here, 2 and 3 up here, and the conclusion is at the bottom. So the conclusion is, oh, let's do this in green. It seems like a conclusive color for some reason. Okay, and let's take out this false and true above, so we have space here. Right, so identify our things here. The conclusion is here. Identify that. I'm not sure why that happened. Okay. Make it a bit far. So that's there. The premises are, there's one here. There's another one here. And R itself is a premise. Okay, so they all lined up nicely, which is helpful. Now, where are all three premises true? I see here in the first row, all premises are true and the conclusion is true. So that's good. Where else are all the premises true? I spot the third row. All premises are true and also the conclusion is true at the same time. All right. And then I see 1, 2, 3, 4, 5. The fifth row, all premises are true. At the same time, the conclusion is true, so that helps us. And the second last row, all premises are true as well, but here the conclusion is not true. So that's not good. So it's just that one little thing that ruins the whole thing, and then it's not a valid deduction rule. That's why we have to be so careful with these. We can get the truth table right, which we did, but then you could lose a mark for not identifying correctly that it's not a valid deduction rule. Okay, all right. Let me just give a few seconds there for you guys to digest that and see if there are any questions. In fact, if you guys want, maybe just take a picture of the solution so I can scroll away for a second while you digest that. I'll give you a little while to take that picture if you're doing that. Okay, it doesn't matter because I'm going to upload this. But what I want to do now is go back here and check it because again, these are very delicate things. I need to make sure it's worked out and see if they give us the same reasoning here. Let me just check quickly. Thus, we have discovered a new deduction rule. They're saying it's valid, which is stressing me out a little bit. And if I first look at rows 1 and 5, these are only rows in which all of the statements. PQ. Okay, sorry guys, let me just see this quickly. They are using if P then Q, if Q then R. They didn't use the Q for some reason. Why is that now? Oh no, they're talking. Oh, okay, no. So what we did is right. The conclusion is false. It's not a valid deduction rule. Okay, they found a separate deduction rule, which is not the question. That's not the point. Okay. Oh God, that was stressful. So the conclusion is false. It's not a valid deduction rule.
Sorry, so I just want to find out. So with them
Yeah.
having this whole big paragraph after the truth table, do we have to also put something in like that as well to get the marks, or do we just show where it was true?
Yeah, good question. So not at all. You don't need to write a long paragraph. If anything, you just need to say the deduction rule is true and maybe put an arrow to show me which rows you've identified to prove that the thing is true, or you can identify them by saying row 1, row 2, row 5 shows that the deduction rule is true. Something like that. Yeah. Okay. Is that
Thank you, sir.
okay? No problem. Okay. Yeah, I hate when they do things like this. Okay, anyway, so it's fine. There was no question saying to identify extra deduction rules. That seems unnecessary. But of course, you can try that as an activity if you'd like to do that. If your brain likes these brain teasers, mine doesn't, so I avoid them as much as I can. Right, so here we get into have enough time to cover these things, which is good. We'll do one example per proof here. So here they tell us that proving something mathematically, in a nutshell, what they're saying here is that it's not always obvious and there's not always a set way to do it. It's kind of like art where you can have some foundational techniques, but at the same time, there's a bit of creative freedom that goes with these things. You have to try and think a little bit. Another way of saying it's a brain teaser, right? You use the foundational knowledge that you have, of course, but at the end of the day, it is a bit of a brain teaser. You have to work it out. So direct proof. Sorry, guys, I think someone's unmuted. Is someone trying to speak to me? All right, there we go. So direct proof, firstly, we're proving implications, right? So forget about all the other molecular statements we learned. Here we are focusing on implications, so something of this form. And this is for the entire proof section. If something, then something, and we try to prove these. And as you can see, it's not very mathematically rigorous the way it's written in this little black box here. The way we would prove something like this is assume P to be true, then explain, 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 therefore Q, right? That doesn't really help much, but the explain, explain, explain just means what they're trying to say is assume P to be true, whatever the statement P is. If we assume it to be true, we can usually write it in some kind of mathematical form or with some kind of structure in it. Like I'm trying to think of an example. What we've learned about even numbers, right? We can write an even number as, let's call it, I don't know, let's call it n as an even number. We can write that as 2 times k, where k is some integer. Z, that weird Z. Yeah, so this is just a way of writing formally an even number. Because again, look at this, no matter what k is, this number is going to be even. I mean, of course, k has to be an integer. We've restricted it to that. Whatever integer you plug into this, you will always get n being even. So k could be 3, for example. 2 times 3 gives us 6. That's even. Plug any k in there, you will always see it gives you an even number. So if p says something like n is even, right? I'm doing this deliberately because this is the first example we have. If p is something like n is even, we have to find a mathematically sound way to write that statement, n is even. That's what I've done here. And then from that, can we manipulate this mathematically, logically, to then arrive at the statement q, whatever that statement might be, right? So since we've gone this far with the n is equal to 2k analogy, let's jump straight into this example here, right? If everything I said doesn't make sense so far, it's okay. We will get it all here. So the thing we need to prove is for all integers, firstly, this for all integers is not really a part of the thing. It's just a way to label the variable n, right? After that, you see the statement happening. If n is even, then n squared is even. So we can clearly see the P and Q here. And always identify this first part, which is not really a part of the if-then statement. It's just giving us information or variable names or restrictions, like it's telling us integers here, integers and n. So make sure you look carefully for the if and the then. All right, that's the first warning. Second warning is maybe sometimes they wouldn't write then. Sometimes they might just say if n is even, comma, n squared is even. Right? That's just a weird, different thing to do with. It's just an English language thing, right? It means the same thing. So you may not see the then, but still be able to identify an if-then statement, right? Just be aware. Sometimes they do that little weird thing. I don't know if it's to try to confuse you, but yeah, I hope you guys get what I'm saying here. All right, so now how do we prove the statement? Again, I'm going to go exactly what they say in this black box above. Assume P to be true. So P we identify here, Q we identify here. So P says n is even. So I will write n as n is equal to 2k, where k is an element of integers, right? We've done this before in some example to write an even number. Okay, so that's P, right? This is P in a nutshell. We've summarized it here. So can I explain, and get to Q? Sure, I can. If I want to show that n squared is even, of P and see what happens. So if I square both sides of this equation, I'll get n squared. On this side, I get 2k all squared. Open that up a little bit more, n squared on this side, and then 2k squared opens up to 2 squared times k squared. Let's open that up a bit more. That becomes 4k squared. Now, is that even? Well, it's not immediately obvious, but what if I pull out a 2 and write this as 2k squared? Right? We can do that. And then it seems to be more obvious now that this is even because 2k squared is some integer. Right? Some integer. So we can write that if we wanted to. We don't have to do this last step, but we can write this as 2 times, I don't know, j, where j is some integer. Right? And we can specify j above if we want to. J is just a substitute for 2k squared. So clearly the form we've reached at the bottom, right here, is the same as the form we started with. And the form we started with assures us that the number is even. So the form at the bottom, 2j, it does the same thing. It assures us that it's even. So we've proven that because n squared is equal to 2j and n is equal to 2k, where k and j are both integers. And so that means if this is even, for sure this is even because they have the exact same form. So that's it. We've proven it. That's what we will need to do here. Okay, so if you want to conclude this with a statement or something, you can say something like, since j is an integer, n squared has the form of an even number, right? Something like that. Okay, so that's the first type of proof. Again, there's more examples you guys can look at, but I'm just doing one per proof because these are not the most common thing to come out in the paper. And if they do, usually the simpler ones come out. Of course, we can't conclude anything for sure, but usually that happens. Okay, proof by contrapositive. So sometimes in trying to prove an implication of the form if P then Q, it becomes difficult. But we've learned before that a contrapositive, which has the form at the bottom here, we've learned that a contrapositive is logically equivalent to the original implication. So if I can write this very loosely like this, the original implication is the exact same as a contrapositive, right? Not Q implies not P. So if we can instead, if we can't find anything to use nicely on this side, we could use this side because they're the same thing, right? So that's the whole point here. So let's look at the example to see if this actually works. Okay, so the statement says for all integers n, so again, that's the part that's not a part of the statement. The first part, it's just giving us information. If n squared is even, then n is even. Is that similar to what, it's like the opposite of what we did above, isn't it? Let's check. Yeah, it's opposite. Okay, so that's interesting. So this says if n squared is even, then n is even. So let's first try to prove it directly like what we did above. That's what the instruction is telling us at the bottom here. Let's call the first part P and the second part Q. Try and prove it directly and see what happens. Okay, apparently it's difficult, so let's see if we get stuck. So if n squared is even, then n is even. So n squared being even means I write n squared is 2k, where k is an element of integers. Okay, so that's p. Can I now prove from this, through the explain part, that n is even? The way I need to do that is now to make an n from this equation. That means I have to take the square root of both sides. And if I do that, n squared equals square root 2k. On this side, I will end up getting n. On this side, I will end up getting 2k. Okay, now does this imply that n is even? Well, it's not immediately obvious, right? So this, I mean, we could try tricks here and make it work, but this is apparently not so easy to do. So we can, right? Of course it's possible. Of course it must work. But the point is it's difficult, so maybe there's an easier way, right? So we're not going to kill ourselves going too far with this. Let's just jump straight to using the method of contrapositive. And to do that, well, what happens is the statement kind of will change. We take the statement which looks like not, so it's not repeat, does contrapositive switch the order? I can't remember. Yes, it does. So we have to get a not Q implies not P statement. So if Q says n is even, not Q will say n is odd. All right, so we'll start with n is odd. That's not Q, and that implies not P. So P says n squared is even. So that will say n squared is odd. Right, that's the opposite. So if P is n squared is even, not P says n squared is odd. So this is the new thing now to prove. If we can prove this, it's as good as proving the original. And that's the thinking behind this. So let's start with an odd n, right? You guys may remember this. We did it at some point before. If you don't, that's okay. I'll write it here. N can be written as 2k, right? If I do that, that means it's even. But if I add 1 to that, it becomes odd, right? Because if you take any even number and add 1 to it, it becomes odd. So this is the trick of how to write an odd number. Of course, again, in this case, k must be an integer. That's the important part. Okay, so this is, which part is this? This is the not q part that we're doing here. Okay, how do we now get to the next part? Well, I guess we have to square both sides of the equation to get to n squared. So here we get n squared. On this side, we'll get 2k plus 1 squared. I'm not sure I can see how this is going to work, but let's try it and see what happens. So here I can write this as 4k squared plus, I'll do this in one go. That's going to be, so first 4k squared, then 2k plus 2k gives me 4k plus 1. Okay, now can we write this as an odd number somehow? Maybe if I factor out, I can factor out 4k, but does it help me? Okay, let's do it first. Factor out the 4k and then see what's left. Left with k plus 1 plus 1. You see, if we had a 2k instead, that might have been more helpful. So let's maybe put a 2 back in. We'll keep a 2k on the outside, put a 2 back in, so 2k plus 2 plus 1. 2k plus 2, this part in the bracket, 2k plus 2 must be an integer, right? Because k is an integer. So this must be some integer, so let's maybe label this as j. So then we can say equals to 2. Let's be careful about that because now I have 2 integers there. So maybe let's put a k back inside as well, because that will still be an integer, right? So again, maybe the last 2 steps are not necessary to go into that detail of taking it down. You could go straight from here to here, but I'm working it out as we go. So this is the real thing happening here. So 2, I'll put a k back in, 2k squared plus 2k plus 1. And yes, this part here is still an integer, right? Because we got k squared is still an integer, and k is still an integer. Adding integers together still gives you an integer. So yes, this is still an integer. So if you can write up here, this is equal to 2j plus 1. And yeah, there we have it. So that means n squared is equal to 2j plus 1. Maybe somewhere on the side we should write what j is because we made that substitution. So right up here, j is equal to 2k squared plus 2k. Yeah, and then that means that the final form we have is the same as the original form. And the original form meant an odd number. So that means the final form also means we've arrived at an odd number. Okay, so somehow we've done it. This one was a bit more, not too bad. Okay, again, so practice with these a little bit and then you will get used to them. But for now, do we have any questions, comments, or complaints or anything? All right, let's check the chat, see if everyone's still alive. Some people haven't gotten marks for assignment 2. Okay, I must check that because they should all be released, not only on ARC, but also on the other system. You guys have some other system where you get marks. It should be there as well. Yeah, if not, maybe I'll just message somebody or let's check what's happening. They should all be visible. Okay, but yeah, I'll check that. Check what's happening. Okay. Why is this thing here 2 times? Oh, okay, it's because this was the space given to do the example. It's the same one. I just squeezed it all into this little space for some reason. Okay, proof by contradiction. I hope there's not a very difficult example here. All right, so proof by contradiction basically means if there's some statement made where a contradiction is enough to show that that statement, which is actually some kind of rule, it doesn't work. It's like someone claims something and then you show that okay, I assume you're right, and if you're right, let me show you that that leads to the incorrect conclusion, not the same one you've given me. So I assume what you said is correct. Assuming that to be correct, I derive something which cannot be possible. Like let's say I derive something that says, I don't know, gravity makes you fly, for example. And that's coming from the initial statement that you made. So that means if the logical steps from your initial statement to the conclusion that gravity makes you fly, it's all logical in between. I haven't cheated. I haven't used any tricks. I've just used logical steps from your statement to the end statement. And that means the end statement should be valid if you were right. So in other words, your original statement was incorrect. That's how proof by contradiction works. It assumes you're right and then checks logically whether we can deduce some nonsense from it. So that's what we're about to do in this example. Okay, so let's see. This says there are no integers x and y such that x squared equals 4y plus 2. Okay, and this does happen on occasion where you get an example which doesn't look like an implication, and that's okay. We may not have to identify the if and then parts. Let's just see here. Is it clear that this is not an implication? There are no integers x and y such that x squared equals 4y plus 2. Usually there's a way to write these as implications, but it may not matter here. So let's just see. Let's assume the original part is right. So again, it says there are no integers x and y such that x squared equals 4y plus 2. So we will assume there are integers x and y. I'm sure that leads to nonsense. Let's see, does that make sense? And how would we show that? Yeah, so let's assume it does exist and show that that leads to some contradiction. So let's label x and y as some integers. Just trying to think, how should we start this? The best way would be x is, we'd have to relabel x. Okay, let's write the equation here. X squared is equal to 4y plus 2. Okay. There are no integers x and y such that the thing is bothering me a little bit. Okay, sorry guys, I don't want to waste too much time. Let me just check here quickly what happens here with this one, because we only have 10 minutes left. I think this is the last one. Okay, we're almost there. We're almost there. Do this one quickly. Where is it? Where is it? So implies that. Okay, so that's the start we need. Okay, there we go. So I guess what they're starting with is, again, we write the statement here, and what they point out is we can pull a 2 out from here, right? 2y plus 1. Okay, which implies that x squared is even, right? Because y is an integer. That's what they tell us. So if y is an integer, this is actually 2 times, I don't know, let's label it something, 2 times j, where j is some integer. So that means x squared can be written as 2j, which we know is even, right? So that's our first little bit of information we can get from the form of this equation. All right, then I think we can make a bit of a leap here based on a previous question. We know that x squared is even, right? We know x squared is even. And if x squared is even, it means that x is also even, right? We've proven this in a previous question. If you're given this in an exam, you have to reprove it, of course, but we just did it, so we will remember this part. So x is even means I can write x itself as 2 times, let me not use j because we use it already. Let's use k. X is 2k, where k is some integer. Okay, so we have a form for x and we have a form for x squared. So let's square this and see if I get back to the form of x squared, right? Maybe that will do something. X squared is equal to 4k squared. All right, this is my new x squared. Okay, let me put this in a different color. This is my new x squared I've deduced at the bottom. This is the original x squared. So the old x squared, okay, let me not write it. The old x squared is 4k squared. Why is this happening? Let's write here. The old x squared is 4k squared. The one above is 2j. And what is j? We've substituted 2y plus 1, where y is some integer. Okay, and on the left we have 4k squared. Have we reached a contradiction? Yes, we have. This is, I think, what we're looking for, because the left is something even, right? Yeah, because we can write it as, okay, let's do this. Let's do this. The left is even because I can write it as 2 into some integer. 2k squared is an integer. And the right is odd because it's an even number plus 1. So this is odd, this is even. So how can something odd and be equal to something even? That doesn't make sense. So this here is a contradiction. Okay. All right, so that's how we would do something like this. Again, you can see why they say there's no set method for all of these things. You have to play around a little bit. it's a bit messy, right? This is why they don't test very difficult versions of these things usually. But off a brain teaser. Okay, I'm glad we got to an answer. There's no guarantee of that here. Okay, so they've given us a claim there are no integers x and y such that x squared equals 4y plus 2. We assume that there are integers that exist, and we got a contradiction, right? So in other words, there must be no integers, because if we assume that to be true, we get a contradiction. Okay, and I'm going to rush through this one because there's no example for this one, so we can get to the last one. Okay, proof by counterexample. It's a situation where someone claims something to be true, right? So what they claim to be true here, where is the thing? Let me just find this quickly in the paragraph somewhere. Okay, it says there is an integer n such that, there's it right here, there's an integer n such that n squared minus n plus 41 is not a prime. So again, this is proof by counterexample, right? So there is an integer n such that n squared minus n plus 41 is not a prime number. There is an integer n such that that is not a prime number. Okay, so what you would do here, again, this is not likely to come out, but you would have to go through all n's and check whether you get something which is not a prime number. So that's what they're doing in this little list at the bottom here. If n is equal to 1, plug n into the equation and get 41. If n is equal to 2, plug that into the equation, get 43, and so on, and keep on going until you find a counterexample. Right, so they're saying there is an integer n such that n squared minus n plus 41 is not prime. So you just have to find that one, right? It exists somewhere here. You just have to look through the list and find it, calculator work, right? So again, this is unlikely to be a thing they'll test because it can be tedious. You could find it on the first go, you could find it on the 5 millionth go, it's one of those things. So that's how you prove by counterexample. You find an example that that basically counters what the thing is saying to show that, again, depending what the claim is, you prove that something is either true or not true, depending how they claim it, right? And the way they'd say it is existential statements can be proven this way, right? There's a little thing here that says that. Okay, now the last one. We have 4 minutes, so let's go with this one. Proof by cases is, again, this one's not too bad, I think. So we have something of the form of an implication. And sometimes it's not clear how to start, but you can break something up into cases and prove it for all the cases, right? So something like this, let's just do the example. For any integer n, that first part gives us some information. Or does it? Yeah, it does. The number n cubed minus n is even. Okay, so it's not exactly an implication, but again, that's not important here. The number n cubed minus n is even. So let's make cases here, right? We don't know anything about n at all, so where do we even start? Let's assume first that n is odd. Then later we will assume n is even, and that's every possible case for n, right? N cannot be anything other than odd or even. So let's prove in both those cases that n cubed minus n is even. Then we're done. Okay. So n is odd. In that case, we'll write n as 2k plus 1. Of course, we know k is an integer. We've seen this before. Then what does n cubed minus n look like? Is it an even number? Well, I don't know. Let's check. So let's plug our n into here. Is there a better way to do this? Maybe I can substitute an n out of it first. N squared minus 1. This really is going to be a bit messy. Anyway, so here we'll get n on the left, 2k plus 1. Inside here we get 2k. Okay, I'm just going to do this in one go, right? Just to save some time. n squared will be 2k plus 1 squared, which is 4k squared plus 4k plus 1, and there's still a minus 1 here. All right, so the first thing I wrote is just n squared. Okay, 2k plus, then here we get 4k squared plus 4k, no, the plus, so that's helpful. Okay, now I can see a k cubed is going to come up here, which is not ideal. That's why I don't like these things. Very much trial and error a little bit. Okay, so let's keep that one side. Let me do the even side here, and let's just see what happens if n is even. If we can get to that one at least. So if n is even, n can be written as 2j, where j is some integer. Okay, so n cubed minus n in this case becomes, again, should I factor this out? Is it necessary? Yeah, let's factor that out. N into n squared minus 1 is equal to 2j into 4j squared minus 1. Okay. Yeah, actually, I think we kind of there, aren't we? I'm just looking at this now. 2j. So what if I pull this j into this thing? Leave this to be 4j cubed minus 1. Because j is an integer, j cubed is also an integer. This entire thing here is an integer. So 2 times an integer is going to be even, right? So that one's good. We've shown this one. We just need to get the left. Sorry, guys, I know I'm out of time already.
I just want to
Yes.
ask, right? When you're taking the j in there, how can you make it go to j cube? Because don't you have to take it, what you do to the one side in the bracket, you have to do to both sides? Like,
Oh, you mean this one here should be a j as well? Yeah,
yeah.
you're right. Yeah.
Okay.
Well, was that the question? Sorry, or did I just make a new question?
No, no, no. That was the question.
Okay, okay. Perfect. Thank you. Okay. So yeah, so the even one is fine because that is an integer. The one on the right somehow must be an integer as well. I'm just trying to work it out here. And if I expand it, it will work out. So guys, I will upload this. So if you guys want to leave already, now I'm out of time. That's perfectly fine. Just bear with me because I'm going to finish this anyway. But again, don't feel bad if you guys want to leave. That's okay. I just need to find a way to make this an even number. Maybe I'll just open up the whole thing and see. Okay, but for those who are leaving, guys, have a good night. Thanks for your attention. I'll see you one more time the next time. I just need to use my head a little bit here. If I open it up, what happens? Let's just open it up. 8k cubed plus 8k squared. This is going to help me. Plus 4k squared plus 4k. Can I write this as 2 times some integer? 2 into 4k cubed plus 4k squared plus 2k squared plus 2k. Oh, there we go. And all of this, everything in the brackets, these are all integers and powers of integers, so it leads to an integer. So this entire bracket here is an integer. So that's perfect. So that means what we reached at the bottom is also even. There we go. So we've proven n cubed minus n is even. If we start with an odd n, and then we've proven it again if we start with an even n. So it means no matter what n is, n cubed minus n is even. Oh, thank goodness we got there. 3 minutes late, but we got there. Okay. Right, guys. I appreciate your attention. I will be here for another 10 minutes or so if you have questions. Let me just check what's happening here. Yeah. Otherwise, I'll see you guys next time for one final revision session. And yeah, thanks, guys, and have a good night. All the best. Oh, yeah, me too.